Good morning. We are today going to talk about wave calculations as they refer to the visible light portion of the electromagnetic spectrum that you guys talked about yesterday in class. So we know a lot about waves. We know that if we're talking about light, that waves are traveling at what we call c, the speed of light. This is a constant value. It goes on and on and on, but we rounded it to 4 significant figures for you today. So the value that we need you to know is the speed of light is 2.998 times 10 to the 8th meters per second. That is roughly about 300 million meters in 1 second. Or 186,000, my comments aren't working this morning, miles per second. Let me give it to you in a perspective. Ready? If I had a light particle right here and I could pinch it between my fingers and hang on to it for a second, and then I said, on your mark, get set, go, and I let this guy go, he could circle the equator of the Earth 7.5 times in 1 second before it got back to me. That is crazy. It wouldn't get back to me. It'd be somewhere halfway around the Earth since it's only 7.5 times. But I wanted you to understand how fast this light is really moving. So we know how fast the light moves, which means that we know c at all times. Then there are 2 other variables we need you to know. My kids tend to call this the long-necked dinosaur. So they refer to this guy as dinosaur even though his name is lambda. This is your wavelength. Well, the key word here is length. We like to measure length in meters. Meters is a base unit. It's nice and pretty. If I give you something like kilometers, centimeters, millimeters, nanometers, you're going to have to convert with a quick little train track. And the reasoning for that is that this is in meters. So since this is in meters, this needs to be in meters also. And my last variable is this weird little V thing. It's kind of like a curvy V. It's called a nu, N-U. We don't care if you know what it's called. We just care that you know that V stands for frequency. And what I tell my kids is high frequency hurts your ears. And so we're going to put an HZ label on the end of our frequency. All that means is the number of waves per second. So if this is your eyeball, I'm an artist, don't be jealous. Okay, how many waves passed by my eyeball in 1 second? That would be the frequency. Sometimes the AP test loves to put things like this, seconds minus 1, just to freak kids out, I think. All that really means is 1 per second. So that means 1 wave per second. And so that is the same thing as hertz. And so I will show you why I like this 1 over seconds when we do our first problem here in just a second. So here's example 1. We are going hunting for nerd words. And so by that I mean I look around and I see a wavelength. And the symbol for that was lambda or dinosaur. Has a frequency of blah, 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 blah. That is my curvy V. Calculate its wavelength. There's dinosaur again. So we go hunting for a formula that has these variables in it. We've only learned 1 formula so far, so we're going to write it down. C is equal to wavelength times frequency. We're going to give you a point for that, so make sure you do this step. Then, we are not like math. We do not want you to start plugging in numbers and then combine like terms. We don't have like terms in science because we have units on all of our numbers, which totally muck up the whole idea of like terms. So it makes it a little more problematic. I'll show you what I mean. So instead, what we want you to do first is rearrange the letters for the variable that we're finding. And they said, calculate this wavelength. So here's what I do. I'm going to put wavelength in a box. I need to isolate wavelength on the side of the equal sign all by himself. So that means I need to get rid of frequency. The way I do that is by doing the opposite. It's currently being multiplied by wavelength, so to get rid of it, I have to divide by wavelength, and it goes away. I don't know if it's because I'm a girl or because I'm a teacher, but I like to make this pretty because now it looks ugly. So I'm going to rewrite this. Wavelength is speed of light over frequency. Now I'm ready for step 3. Let's plug in our numbers. Well, we said a moment ago up on top of your page that c is equal to the speed of light. 2.998 times 10 to the 8th meters per second. We're going to divide that by the frequency, which they happen to give us as 4.51 times 10 to the 16th hertz. Now, as a scientist, my brain automatically goes here and says, uh-oh, there's nothing to cancel out. Did I plug something in wrong? And the answer is no. If you remember what we said a minute ago about hertz, we said that it's the number of waves per second. So look at this number. It's astronomically huge. I don't even know what it is. There's so many decimal places. So 451 zillion waves per second are passing by my ear. So that means this hertz, or 1/2 can cancel with this second up here in the denominator. So I'm going to cancel that, and I'm going to cancel all of that, leaving me with this m for meters. Well, if I go back and say, what am I finding? Well, I'm finding the wavelength. So it makes sense that the wavelength would equal 6.65 times 10 to the negative 9th meters. You might want to practice putting these times 10 to the into your calculator again. 2.998 E8. No times, no 10. Divided by 4.51 E16. And voila, we get a wavelength in meters. So how could we ruin your life? So take a look at this one. We hear some nerd words, quantum and energy, but we don't have symbols for those, and so we're going to ignore those for now. These have a wavelength of 414 nanometers. So we're going to label that as our dinosaur. This time we are finding the frequency, which is the curvy V. We're going to rewrite that formula. C is equal to lambda times V. This time we're going to put a box around the V. Since we want the frequency, we've got to get rid of this lambda who's next door. They're currently being multiplied, so to get rid of it, I divide. And we get our frequency is the speed of light over the wavelength. So now we start plugging in what we know. The speed of light is the same every day. It's really freaking fast. 2.998 times 10 to the 8th meters per second. We're going to divide that by the wavelength. Now don't write this down because it's going to be wrong. I'm going to put it there anyway just to show you what I mean. 414 nanometers. Well, I always check my letters and say, did I set this up right? Here's how I know I can't do this. See, this is meters. This is nanometers. Even though they're related, they're not the same. So I can't divide them because they're not the same unit. So I'm going to have to get rid of this 414 nanometers. And I'm going to have to come down below. I'm going to have to change it into meters. So nanometers goes down, meters goes up. I would say, who's larger, a meter or a nanometer? Definitely a meter. So we say he gets the 1. The big guy gets the 1. The little bitty guy, I want to know how many little bitty nanos are in that meter. Thank God my killer had drugs because he was doing cocaine and meth under Nana's porch. And so 1, 2, 3, 6, 9, 12. So guess what, folks? Nano means 9. So then we find out that that is 4.14 times 10 to the negative 7th meters. This value will then plug in to my wavelength location, 4.14 times 10 to the negative 7th meters. This makes my little scientist brain happy because I can get rid of meters and meters, giving me that funky seconds. Now you have to be careful, that seconds is on the bottom. So because the seconds is on the bottom, the answer is not in seconds because that would be time. We're not solving for time, we're solving for frequency. I didn't really leave room for my answer, so I'm going to get creative and come way over here with it. So when I plug that into my calculator, I get 7.24 times 10 to the 14th. And I'm going to put hertz on that. If I wanted to, I could put 1 over S on that answer as well. Put a big box around your answer so we can find it. There was a lot going on this slide. So that's how we can ruin your life. Make you do a little train track, make you recall these numbers, 2-step problem. If you will do us the favor and put those letters on the end of all your numbers, it tells the story and tells you what to do. Don't skip that crucial step. So now we have a new formula. This one's pretty easy. We've got a big capital E. That big capital E is always going to stand for energy of a quantum. A quantum is just a packet, an itty bitty little teeny tiny packet of energy. Energy travels in these little packets or finite quantities called quantums. A photon is specific to a light quantum. So it's a little bitty packet of light. If it's little bitty, then you can expect these numbers here for E to be itty bitty, like something like 10 to the negative 19th. And we measure those guys in joules or J. It's a dead guy's last name. Then speaking of dead guys, we've got this other one. Max Planck, he was the one that basically figured out the photoelectric effect, the reason why something glows red hot when it gains too much energy, like a horseshoe or an oven coil. And so he came up with this constant that figured out the relationship between the frequency, which we already know in hertz, and the energy of those photons. So basically, if I know the frequency, I automatically know the energy using Planck's constant of 6.626 times 10 to the negative 34th joule seconds. Notice that's a dot in between the J and the S, meaning they're being multiplied. You don't have to know what it means. You don't have to understand where it came from. It's just the correlation between this frequency and this energy. It's the connector that gets us from one side of the equal sign to the other. So nothing has changed here. So let's see how this works. We want to calculate the energy of a photon. So there's my nerd word. We now know that that gets a capital E. Here's another nerd word, photon, but we didn't learn a special symbol for him. We've got yellow light. They're just trying to tell you what color you are calculating. It doesn't mean anything to you though. And we've got this frequency of all this jazz. That is your V. So we choose a formula. Well, here it is up here. It's our new one. E is equal to H times nu, or frequency. We are trying to find in this guy, calculate the energy. I need energy to be on the side of the equal sign by itself. Well, look, friends, it is. I see kids every year do something freaky with this and start multiplying and dividing and rearranging this when all you got to do is plug in. So we are ready to rock and roll. So that means I need H 6.626 times 10 to the negative 34th joule seconds. Practice saying that a whole bunch of times fast. You'll sound like a nerd. It's awesome. All right. And we want to plug in that frequency. 2.73 times 10 to the 16th hertz or 1 over seconds. So I take a look at my formula here and I look at my units. I've got JS and I've got 1 over S. So since seconds is in the numerator here and in the denominator here, including that hertz, seconds can cancel with all of that, leaving me with joules, which is a good thing because I'm about to solve for energy. Energy is always measured in joules. Now, remember what we talked about before we look at this answer. We said we're calculating the energy of a teeny tiny photon, which is so small I can't even show you. So we're expecting a teeny tiny answer. So my fancy calculator gets 1.80 times 10 to the negative 17th joules. So a teeny answer, just like we expected. Oops. So that's a little too easy, right? Let's pick it up a notch. So now, find the nerd words, calculate the frequency of a photon of blue light this time. So it's different than yellow light, and it's got an energy of this. So we write our equation. E is equal to H times V. We're calculating the frequency. So we've got to get rid of the H. So we do that by dividing. We make it pretty on the other side. Frequency is energy over H. We plug in our energy. 2.48 times 10 to the negative 14th joules. And we're going to divide that by H, Planck's constant, 6.626 times 10 to the negative 34th, with that weird unit called a joule second. We figure out what they have in common, and we cancel them out. Joules and joules. Which leaves us seconds, but if you extend this, it really leaves you seconds underneath the fraction, which is where we want it. And my calculator gives me an answer of 3.74 times 10 to the 19th 1 over seconds, or hertz, whichever one you prefer. So a little formula manipulation there, but nothing too crazy, nothing too hard. We do want to watch our sig figs. We don't ever look at the constants like the speed of light or h for our sig figs. We always look at what's given up in the problem. They gave me 3 here, so I need 3 on my answer. So it can't always be this easy, right? We've got to find a way to make this pre-AP and ruin your life. So we came up with this last example here to do that. So this says we've got a laser in a CD player, if y'all remember what those are. Back before all digital music, we had CDs. Stands for compact disc, if you didn't know that. Uses a light with a wavelength of. So there's my first nerd word right there. And so I've got dinosaur. What is the energy? E of this single photon. Now here's my problem. I go up to my equation and I'm looking for dinosaur and E. Well, I see him, but the lambda is definitely not there. But we learned an equation earlier that had that. So maybe I should be using this equation. So I go and I find, and I'm like, yes, this has lambda, but it doesn't have an E. So how am I going to get from one equation to the other? Well, it's actually quite simple. If you'll notice, both equations have frequency in common. So since they gave us the wavelength here, we're going to start with the wavelength equation and solve it for V. So we're going to do that first. C is equal to wavelength times frequency. I don't know this, So I'm going to get rid of the wavelength over here. So frequency ends up being c over wavelength. My c is the speed of light. It hasn't changed. But my brain takes a look at this and says, uh-oh, nanometers again. So I'm going to have to go and I'm going to have to switch that into nanometers. So I come down here to do that real fast. 7.80 times 10 to the 2 nanometers. 1 times 10 to the 9th nanometers in a meter. Which gets me 7.80 times 10 to the negative 7th meters. So I'm going to plug that right up above. 7.80 times 10 to the negative 7th meters. My science brain is happy, happy, happy because I can cross out meters and get seconds in the denominator. This gives me a frequency of 3.84 times 10 to the 14th, 1 over seconds, or hertz, whichever one you like. Now, this is awesome, except this is not what they asked us for. They asked us for the energy of the single photon. Well, we're closer. Here's why. We used our wavelength to find frequency. Now we've got a number to plug into the energy equation to get us that value for E. So I write my second equation. E is equal to H times frequency. I'm trying to find energy, so I don't have to change anything or move anything, which is awesome. I plug in my Planck's constant of 6.626 times 10 to the negative 34th joule seconds. And then I multiply that by the frequency. So it's going to come down here. 3.84 times 10 to the 14th, 1 over seconds. My little nerd brain says, oh, seconds in the numerator cancels with seconds in the denominator. I'm left with J. So my final answer ends up as 2.55, I had to round up, times 10 to the negative 19th joules. That is basically everything we've learned. Scientific notation, that is both energy formulas, that is thank God my killer had drugs with metric conversions. There's a lot going on here, and sig figs. So this is a very important problem to understand. We don't want you to be little robots and memorize everything. We want you to understand what you're doing and make it make sense. And so just remember that these two equations are both connected by that frequency, and use one formula to get you what you need in the other formula. And always, 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 always check these units. It tells the story of where you're headed, and make sure that you don't make any mistakes. Have a great day. Good luck on the Wacky Waves homework. Get it started right now. Do as much as you can, and both of your teachers will be available for tutorials at lunch and after school today, so stop by.